So let's do an example problem. If we have a 0.4% carbon steel at a temperature just below the eutectoid, what's the composition of iron carbide and ferrite? And then out of 100 grams, how much cementite forms and how much perlite and proeutectoid ferrite do we have in the 100 grams? So we start by looking at the ends of the RS tie line, and we could pick off the endpoints. So the carbon content of ferrite right here is 0.022, and the carbon content of cementite right here is 0.67. I'm sorry, 6.7. And then we'll use the lever rule with the tie line, calculate the amount of iron carbide. It's going to be the portion of the tie line R over the total, R plus S, which works out to about 0.06 weight fraction of cementite. And then multiply that by 100 grams, and it's 5.7. So that's a different question than how much perlite. So there's a difference between how much cementite and how much perlite is in the microstructure. Okay, so to actually calculate how much perlite, we have to go just above the 727 degrees C and calculate how much proeutectoid ferrite and how much austenite we have with this VX tie line. Okay, we have our endpoints. The nominal composition we said was 0.4% carbon. Okay, we got that. And then our ferrite, again, has a maximum of 0.022% carbon, so that's the endpoint of the VX tie line. And then the right side, the endpoint of the X tie line, is 0.76 weight percent carbon because that's our eutectoid. So those are the 3 points that we needed to know to figure out this problem, because the weight fraction then of perlite, meaning the weight fraction of austenite, is V, the opposite side from the austenite, over V plus X. And that would be C naught minus C alpha up here, divided by C gamma minus C alpha up above that we already identified. So we just plug and chug, and we get that our microstructure is going to be about 0.51 fraction perlite, which is the same as multiplied by 100 for 100 grams, 51.2 grams of perlite in that 100 gram sample. So suppose you don't know the carbon content of the steel, but you have the microstructure and you see that it looks equilibrium and it's about 40% perlite. Can you figure out the carbon content of the steel? Well, yes, we can. We just rework the equation using our knowledge of the carbon content of the perlite, the carbon content of the ferrite in equilibrium, and we can work our way back to figure out the carbon content of the steel. So starting off with the carbon content of the perlite, we know that the perlite transforms from austenite at the eutectoid, so the perlite is 0.76% carbon. And then the carbon content of the ferrite, since it's saturated, is going to be 0.022% carbon. So what's the carbon content of the steel? Well, I know that it's 40% perlite. So if 40% of the microstructure is 0.76% carbon, I just multiply those two and I get that there's 0.30% carbon that's contributed by the perlite phase. So how much is contributed by the ferrite phase? Well, 60% of the microstructure is ferrite, and I know that the carbon content of that ferrite is 0.022, so I multiply those two, and I get that 0.01% of the carbon in the steel is contributed by the ferrite phase. Add those two up, so I have 0.30% carbon contributed by perlite, 0.01% carbon contributed by the amount of that 60% ferrite in my microstructure, and I get that the overall carbon content, the C naught, is about 0.32% carbon. So if I solve the lever rule equation for carbon, knowing that the eutectoid carbon content, that's the amount of carbon in the austenite that transforms to perlite, is 0.76, and knowing that the amount of carbon in the ferrite is 0.02, then I can just easily graph that and be able to figure out the carbon content of the steel by the perlite. So if I'm looking at a microstructure, I analyze it, and it has about 30% perlite, which is not uncommon for line pipe steels. Then I can use this expression to estimate that we might have somewhere around 0.25% carbon. This graph over on the right just zooms in on the area of interest, about 0% to 40% perlite, where we're going to find most of our line pipe steels. So why would I care about trying to figure out the carbon content from the amount of perlite in the microstructure? Well, carbon has important effects on the mechanical properties. It increases the strength, as we have seen, and it can decrease the toughness, and it can also decrease the weldability. So if we look at this chart from azom.com, as you increase carbon content, you take a hit on impact energy fairly significantly as you increase the strength in terms of tensile strength and yield strength. Now, let's look closer at that impact energy, because that doesn't just depend on carbon content, that also depends on temperature. So as you change the carbon content, here are several carbon contents that are of interest for our line pipe steels. As I change the carbon content, I change the plot of toughness impact energy, or the amount of energy that the steel can absorb versus temperature. What's that mean? So if I look at this 0.31% carbon steel, I see that if I have that steel at 100 degrees Celsius, it's going to absorb somewhere around 80 or 90 joules of energy. That's good. That's tough. We like steel that is tough, can absorb energy, and will not fracture easily. Now, as I move down that curve, let me change colors, and I start trying to break my steel sample at lower and lower temperatures, when I get past about, let's say, 25 degrees C, now I'm below 50 joules. Now I'm getting into more brittle behavior, which is typical of of steels. And I don't want that. So one way to combat that brittle behavior is lowering the carbon. Choose a different color. So this 20% carbon, now I have a higher upper shelf energy, so even more toughness at high temperatures, and a transition, we call this a transition temperature, to brittle behavior at even lower temperatures. Now it's below 0 degrees Celsius. Now if I lower the carbon content even more, this 0.11, poor color choice, you can't see it anymore, but that's 0.11% carbon. Now I have a very high toughness at most of the temperature range, along most of the temperature range, and then a very low ductile brittle transition temperature of negative 50 degrees Celsius approximately. So what does that tell us about carbon content? It reiterates that carbon content decreases the upper shelf energy. An increase in carbon content decreases the upper shelf energy. And increases the ductile to brittle transition temperature. So an increase in carbon impacts us in two negative ways in terms of toughness.